Picture two coins. You flip them both at the same time in two different rooms 100 miles apart. One lands heads. The instant it does, the other lands tails. Every single time. No signal passes between them, no wire, no radio wave, no light. Nothing. And yet they always match, always the opposite. Every flip, every room, every distance. That is not a metaphor. That is a real experiment. Scientists have done it. They have done it with particles instead of coins, and the results are the same. The universe behaves this way whether we like it or not, and some of the biggest names in physics are now asking a question that sounds almost impossible. What if this is not just a strange feature of particles? What if the entire universe, every atom, every star, every galaxy, every piece of space itself, is tied together in one single enormous web of these connections? This is the story of quantum entanglement, where it came from, what it actually is, what the experiments show, and why some physicists now believe the whole universe might be one giant entangled system, always and forever. The science took almost 90 years to get here. It started with an argument between two of the greatest minds who ever lived, and the universe turned out to be stranger than either of them believed. If you want more documented science like this, subscribe now. It is the best way to support this work. Also drop a comment with what city you're watching from. This script is built on peer-reviewed research from journals like Physical Review Letters and Nature, including landmark experiments by Alain Aspect in 1982, and the Bell test experiments confirmed again in 2015 by teams in Delft, Vienna, and Boulder. Now back to the science. The story starts in 1935. Albert Einstein was not happy. Einstein had spent 30 years reshaping physics, but quantum mechanics bothered him deeply. The theory said that particles do not have definite properties, like position or spin, until you actually measure them. Before the measurement, a particle is in a blur of possibilities. Einstein hated this. He believed the universe was real whether anyone looked at it or not. He called the alternative spooky action at a distance, and he meant it as an insult. In 1935, Einstein worked with two other physicists, Boris Podolsky and Nathan Rosen. Together they wrote a paper. The paper is now called the EPR paper, using the first letters of their names. Their argument was careful. They said, suppose you have two particles that interact, then fly apart in opposite directions. Quantum mechanics says that the spin of each particle is not decided until measured, but the moment you measure one and find it spinning up, quantum mechanics says the other must instantly be spinning down, no matter how far away it is. Einstein said this was absurd. Either the particles secretly carried that information all along, hidden from us, or something was reaching across space faster than light. Both options were, to Einstein, unacceptable. He concluded that quantum mechanics must be incomplete. There must be hidden variables, secret pieces of information the theory was not seeing. For almost 30 years, this was mostly a philosophical argument. Then, in 1964, a physicist in Geneva named John Stuart Bell did something remarkable. Bell turned the argument into math. He wrote a short paper, only 6 pages long, published in a journal called Physics. Bell proved that if Einstein was right, if hidden variables were carrying the instructions for how particles behave, then the results of certain measurements would follow a strict mathematical limit. He wrote out the inequalities. If you ran the right experiments and collected enough data, the numbers would stay within a boundary if Einstein was right. They would break that boundary if quantum mechanics was right. Bell's theorem was a test, a real, concrete, experimental test. For the first time, the question had an answer that could be found in a laboratory. This was remarkable because, for decades, smart people had assumed the debate between Einstein and quantum mechanics was purely philosophical, the kind of thing you argued about over coffee but could never actually settle. Bell proved them wrong. He took an argument about the nature of reality and turned it into a number. Either the number stays inside the line, or it breaks through. No interpretation needed, just data. Bell himself was cautious about what his result meant. He spent years refining the theorem, pointing out the loopholes experimenters would need to close, and thinking about what it would mean if quantum mechanics really did win. He worked at CERN in Geneva, the same laboratory that would later discover the Higgs boson. He was known for asking uncomfortable questions that others preferred not to think about. He once wrote that the concept of measurement in quantum mechanics was so vague and ambiguous that it was not possible to formulate the theory in a logically clean way. He wanted physics to be clear. Bell's theorem was his way of forcing clarity on the universe itself. The experiments began arriving in the 1970s. The first serious attempt came from Stuart Friedman and John Clauser at the University of California, Berkeley, in 1972. They used pairs of photons, which are particles of light, and they measured whether the correlations between the photons obeyed Bell's limit or broke it. Their data broke the limit. Quantum mechanics was right, but the experiment had gaps. Clauser's detectors were not efficient enough. There were loopholes that a determined skeptic could exploit. Then came Alain Aspect. Aspect was a French physicist working at the Institut d'Optique in Orsay, just outside Paris. Between 1980 and 1982, He ran a series of 3 experiments. Each one closed a different loophole. The final experiment, published in 1982 in Physical Review Letters, was the clearest demonstration anyone had produced. Aspect and his team used calcium atoms to generate pairs of entangled photons. They sent each photon toward a different detector, separated by about 12 meters. Then, while the photons were in flight, they randomly switched the settings on each detector. This was critical. If the particles were somehow communicating, they would need to send a signal faster than light to coordinate their answers. The switching happened so fast that no signal could travel between detectors before the measurement was made. The result? The correlations still broke Bell's limit. By far. The numbers matched quantum mechanics exactly. The hidden variable idea was not completely dead. Determined physicists pointed out 2 remaining loopholes. The first was the detection loophole. If detectors only catch some photons and miss others, maybe the ones they catch are a special biased sample. The second was the locality loophole. Even in Aspect's experiment, the detectors were only 12 meters apart. Critics argued that maybe some unknown influence could still sneak between them at speeds below light speed. Over the next 3 decades, physicists worked to close both loopholes in the same experiment. The year 2015 was when it finally happened. 3 separate teams, working independently, each closed both loopholes at once. The team, in Delft, Netherlands, led by Ronald Hansen at Delft University of Technology, used electron spins trapped in diamond crystals. The 2 detectors were 1.3 kilometers apart. The team ran 245 trials. The results broke Bell's inequality decisively. The detection loophole was closed. The locality loophole was closed. The same year, teams in Vienna and Boulder, Colorado, ran their own loophole-free tests and got the same answer. Quantum entanglement is real. It is not a trick. It is not hidden variables pretending to be mysterious. The universe genuinely does this. Subscribe if you want more documented history of science like this. Comment your city. Back to the story. So what exactly is happening? This is where the explanation gets both simpler and stranger than most people expect. When 2 particles become entangled, they are not secretly passing notes. They are not connected by a wire we cannot see. The best description physicists have is that the 2 particles stop being separate objects. They become one system, described by a single set of probabilities, even when separated by large distances. When you measure one particle, you are not sending a signal to the other. You are simply learning something about the joint system. The other particle's state becomes definite at the same moment because there was never a definite state for either particle on its own. The whole system collapses at once. Think of it like this. Imagine you write the word hot on one piece of paper and the word cold on another piece of paper. You seal them in envelopes, shuffle them, and mail one to Tokyo and keep one in New York. When you open your envelope and see hot, you instantly know the envelope in Tokyo says cold. No mystery, no spookiness. The information was always there. But that is not what quantum mechanics says is happening. In the quantum version, neither envelope has a word written in it until one of them is opened. The act of opening one envelope creates the word in both envelopes at once. This is what Einstein refused to accept. This is what the Bell tests proved is actually happening. The particles do not carry hidden information. They genuinely have no definite state until measured. And when one is measured, the other snaps into a matching definite state instantaneously, regardless of the distance between them. This does not allow faster than light communication. Here is why. When you measure your particle and get a result, you cannot control what result you get. The result is random. You cannot encode a message in a random outcome. Your partner at the other detector also gets a random result. Only when you call each other afterward and compare your results do you see the correlation. The comparison requires a regular phone call or email, which travels at or below the speed of light. So no information actually travels faster than light. The strange correlation exists, but it cannot carry a usable signal. Einstein was wrong about hidden variables, but he was right that something deeply weird was happening. The question physicists have spent the last 60 years asking is, how deep does this weirdness go? The answer, emerging from experiments and theories built between 2000 and 2025, is much deeper than anyone originally thought. Here's the first clue. In 2006, physicists began taking seriously a theoretical idea about the structure of space itself. The idea connects 2 things that seem completely unrelated: quantum entanglement and the geometry of space. In 2010, Mark van Ramsdonk, a physicist at the University of British Columbia in Vancouver, published a paper that started a firestorm. Van Ramsdonk was working with a theoretical framework involving something called the Holographic Principle in anti-de Sitter space, which is a mathematical model of a universe with a specific kind of curved geometry. He showed that in this framework, entanglement between particles on the boundary of a region of space was directly connected to the geometry of that region's interior. When you reduced the entanglement, the regions of space began to pull apart. When you removed all entanglement, the regions of space disconnected entirely. Van Ramsdonk's conclusion was startling. Entanglement might not just be a property of particles sitting inside space. Entanglement might be what holds space together. The fabric of space itself might be woven from entangled quantum threads. This sounds like wild speculation, but it is grounded in serious mathematics. The framework Van Ramsdonk used is called the ADS-CFT correspondence, proposed in 1997 by Juan Maldacena at Harvard University. The ADS-CFT correspondence is one of the most cited papers in the history of physics. It has been cited more than 20,000 times in peer-reviewed literature. The framework is a precise mathematical tool that many physicists use to solve problems in quantum gravity. Van Ramsdonk was not making up metaphors. He was doing calculations. The idea was sharpened in 2013 when physicists Juan Maldacena and Leonard Susskind at Stanford University published a paper connecting two things that physicists had thought about separately: wormholes and entanglement. Wormholes are hypothetical tunnels in space that connect two distant regions. Entanglement is the quantum connection between particles. Maldacena and Susskind argued mathematically that these two things might be the same thing at different scales. They called the idea ER equals EPR. ER stands for Einstein-Rosen bridge, which is the technical term for a wormhole, from a 1935 paper by Einstein and Nathan Rosen. EPR stands for Einstein, Podolsky, and Rosen, the same three authors whose 1935 paper started the entanglement debate. Both papers were written by Einstein in the same year. Maldacena and Susskind were suggesting that Einstein accidentally discovered the two faces of the same phenomenon. If ER equals EPR is correct, then every pair of entangled particles is connected by a tiny microscopic wormhole. And since particles can be entangled with many other particles at once, the whole network of these connections could form the scaffolding of space itself. Now push this further. If space is made of entanglement, and if entanglement can exist across the whole universe, then the question becomes, how much of the universe is entangled with how much else? The answer, based on experiments and theory, is more than you think, and possibly everything. Here is why. In the very early universe, the first fractions of a second after the Big Bang, all the matter and energy in the observable universe was packed into an unimaginably small, dense, hot region. Everything was touching everything else. Every particle was interacting with every other particle. In quantum mechanics, when two particles interact, they have a chance to become entangled. In the extreme conditions of the early universe, interactions were happening at a ferocious rate, at temperatures measured in the tens of trillions of degrees, in a region that would eventually expand to become everything we see today. To give you a sense of scale, the entire observable universe, everything we can see with our most powerful telescopes, everything within about 46 billion light years in every direction, all of it began as a region smaller than a proton. A proton is about 1/10,000,000th of a millimeter across. The visible universe, 100 billion galaxies, each containing hundreds of billions of stars, each star separated from its neighbors by light years of empty space. All of it fits inside something smaller than you can see with any microscope. In that unimaginably tiny region, at unimaginably high temperatures, everything was entangled with everything. There was no room for separateness. There was no distance to separate particles. Quantum connections were being built at every point, at every moment, in every direction. Then space expanded. The region stretched. Distances grew. And what had been in contact separated. What had been neighbors became strangers, separated by light years. But the entanglement built during those first moments did not simply stop. Entanglement does not fade with distance. It does not have a range limit. The connections built in the first fractions of a second are, in some form, still present in the universe today. The particles that formed the early universe did not just interact once and separate cleanly. They interacted in dense cascades. Quantum field theory, which is the modern description of particles and forces, tells us that those early interactions created entanglement, vast amounts of it. As the universe expanded and cooled, particles separated and stopped interacting directly. But the entanglement they had built up during those early moments did not disappear. Quantum entanglement does not fade over time on its own. It can be disrupted by new interactions, but it does not simply weaken the way a signal fades over distance. The implication is that the universe we live in today is threaded with entanglement left over from its own birth. Every atom, every molecule, every star, every galaxy carries the residue of connections built in the first moments of existence. We cannot easily trace all of those connections. The entanglement has been shuffled and redistributed by billions of years of interactions, but it has not been erased. This is not just theoretical hand-waving. There is observational evidence. The cosmic microwave background is the faint glow of light left over from 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. This light reaches us from every direction, and its temperature is almost perfectly uniform, varying by only about 1 part in 100,000 across the entire sky. This uniformity is a problem. Regions of the sky that are more than 2 degrees apart in our view were, at the time this light was released, so far apart that no signal traveling at the speed of light could ever have connected them. They should not know about each other's temperature, and yet they match. This is called the horizon problem, and it is one of the major puzzles of cosmology. The standard solution is inflation, which is a period of extremely rapid expansion that stretched a tiny quantum region into the entire observable universe in a fraction of a second. Inflation would explain the uniformity because it starts everything from the same tiny patch. But inflation also has a quantum mechanical side. The tiny fluctuations in that original patch, the quantum jitter of the vacuum, would have been stretched along with space. Those fluctuations are the seeds of every galaxy, every cluster, every structure in the universe. And those fluctuations were quantum in nature, meaning they were subject to quantum correlations from the start. Researchers, including David Sloan at the University of Oxford, and others have studied what the quantum correlations in the inflationary vacuum imply for the large-scale structure we see today. Their work suggests that the large-scale correlations in the universe, the way galaxies cluster together across hundreds of millions of light years, may carry the imprint of quantum entanglement from the inflationary period. The structures we see through telescopes might be the stretched shadow of quantum connections that existed when the observable universe was smaller than a proton. In 2017, a team led by physicists at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, published results looking at the polarization of light in the cosmic microwave background and asked whether those patterns were consistent with quantum correlations of the type Bell's theorem tests. They found that the correlations in the cosmic microwave background are consistent with quantum entanglement at cosmological scales. The universe's largest observable structure bears the statistical signature of quantum connections. The deepest version of this idea comes from a direction most people would not expect: black holes. In 2012, 4 physicists, Ahmed Almheri, Donald Meroff, Joseph Polchinski, and James Sully, all working in the United States, published a paper that detonated a bomb inside theoretical physics. Their paper is known as the AMPS paper, using the first letters of their names. AMPS pointed out a catastrophic conflict. The rules of quantum mechanics say that information cannot be destroyed. The rules of general relativity, Einstein's theory of gravity, say that an astronaut falling into a black hole should notice nothing unusual at the event horizon, which is the point of no return. These two statements cannot both be true. If quantum mechanics is right, then the information carried by anything falling into a black hole must eventually escape, as the black hole evaporates by radiating energy over a very long time, a process called Hawking radiation, after physicist Stephen Hawking, who described it in 1974. For that to work, the radiation escaping the black hole must be entangled with the stuff that fell in. But for general relativity to be right, the infalling astronaut must not be hit by a wall of high-energy radiation at the horizon. AMPS showed that you cannot have both. One of the foundational principles of physics had to break. This conflict, called the firewall paradox, has been the central problem of theoretical physics for more than a decade. The attempts to resolve it have driven physicists to take the ER equals EPR idea very seriously. If every entangled pair of particles is connected by a tiny wormhole, then the entanglement between Hawking radiation and infalling matter is a network of wormholes threading spacetime. The geometry of spacetime near a black hole becomes a dense tangle of quantum connections. The horizon is not a sharp wall, but a complex quantum structure built from entanglement. In 2019, 2 independent groups published papers in the Journal of High Energy Physics that showed, for the first time in a controlled theoretical calculation, that information could escape from a black hole without a firewall. The key ingredient was entanglement. The calculation used a quantity called the Page curve, predicted by physicist Don Page in 1993. Page predicted that the entropy of a black hole, a measure of how much information has been scrambled, should first rise and then fall as the black hole evaporates, forming a shape like a mountain. For 26 years, no one could derive this curve from first principles. In 2019, researchers did it, using the geometry of entanglement in the same ADS CFT framework Van Ramsdonk had used. The universe's bookkeeping, keeping track of every bit of information that has ever fallen into a black hole, is done through entanglement. The picture that emerges from all of this research is not just that entanglement is a quirky property of some particles. It is that entanglement may be the basic infrastructure of reality. Space is not a stage on which quantum mechanics plays out. Space might be built from quantum connections. Matter might be nodes in a network of correlations. The geometry of the universe might be the large-scale shadow of a vast web of quantum entanglements laid down in the first moments of time and never erased. This changes how physicists think about distance itself. In the usual picture, distance is simple. You are over there. I am over here. The space between us is empty until something crosses it. But if space is made of entanglement, then distance is not a gap between things. Distance is a description of how weakly entangled two regions are. Things that are far apart share very little entanglement. Things that are close together share a great deal. Wormholes, which connect distant regions directly, would be regions of unexpectedly strong entanglement, bypassing the usual geometry. And the smooth, continuous space we experience every day would be the large-scale average of a vast quantum network, just as the smooth surface of a lake is the large-scale average of countless individual water molecules jostling against each other. What does this mean for the universe we actually live in? It means that you, sitting wherever you are reading this, are part of a connected system that extends in all directions without a clear edge. The atoms in your body were forged in stars. Those stars formed from the same primordial gas that formed all other stars and all other galaxies. That gas came from the early universe, where quantum fluctuations were entangled across the same tiny region before inflation stretched it outward. The light that reaches your eyes from a galaxy 2 billion light-years away left that galaxy when the only life on Earth was single-celled organisms floating in shallow seas. The correlations in that light are the statistical descendants of quantum correlations laid down before stars existed. This is not mysticism, it is not metaphor. It is what the mathematics says. It is what the experiments confirm at smaller scales. The question of whether it holds all the way up to the full scale of the observable universe is still open. There is a reason physicists do not yet call this a finished theory. The work on entanglement and space-time geometry is still theoretical. The tools to directly test it at cosmological scales are still being built. But the direction of the evidence, from Bell tests in 1982 to loophole-free experiments in 2015 to the derivation of the Page curve in 2019, runs in one direction. There are researchers today building what is called a tensor network, which is a mathematical structure that models space-time as a web of entangled quantum states. Brian Swingle, then a graduate student at MIT in 2010, showed that a specific type of tensor network called a MERA, which stands for multi-scale entanglement renormalization ansatz, reproduces the geometry of hyperbolic space, exactly the geometry that appears in the ADS CFT framework. This was not a coincidence. Swingle argued it was a glimpse of how space actually works. Space is built by entanglement the same way a MERA is built by entanglement, layer by layer, scale by scale. The deep structure of the universe, below the level of atoms, below the level of quarks, at the level where quantum gravity operates and no experiment has yet reached, may look like a vast network of entangled nodes, each connected to its neighbors by quantum correlations, each correlation contributing a tiny piece of the geometry we experience as space and time. In 2023, researchers at the Google Quantum AI Lab published a paper in Nature describing an experiment on their Sycamore quantum processor. They simulated a wormhole using a small number of entangled quantum bits. The experiment was not a real wormhole in physical space. It was a quantum simulation of the information theoretic properties of a wormhole using 9 qubits. But the fact that a wormhole's behavior could be captured by entangled qubits, and that sending information through the simulated wormhole worked the same way as quantum teleportation through entanglement, was a concrete demonstration that the ER equals EPR idea captures something real about how physics works. The experiment was small. 9 qubits is nowhere near the scale of a real black hole, but a decade ago, physicists could not have simulated even a tiny piece of this. The experiments are growing. Quantum processors are doubling in qubit count every few years. The theoretical predictions are becoming more precise. The tests are coming. Here's the hardest part of this to hold in your mind. If entanglement is the structure of space, then the universe does not consist of separate things that occasionally influence each other. The universe is one thing. The separation we see between objects is real at the level of everyday experience. You're not going to walk through a wall because you and the wall are part of the same quantum system. The effects of this underlying unity are almost completely hidden from us at everyday scales, washed out by the enormous number of particles involved and the constant churning of interactions. But at the deepest level, the level of quantum fields and geometry, separateness is an approximation. Connectedness is the baseline. John Bell, the physicist who made all of this testable, died in 1990 from a cerebral hemorrhage. He died the same year, 1990, that the Nobel Committee was reportedly considering him for the prize. He never received it. He's buried in Geneva, near CERN, where he worked. His theorem is carved into the foundation of everything that followed. In the decades after his death, his 6-page paper became one of the most important documents in the history of science. The experiments it enabled changed physics forever. The ideas it unleashed are still spreading outward, reaching into black holes and the structure of space in the first moments of the universe's existence. Alain Aspect, whose 1982 experiments were the first decisive evidence, shared the Nobel Prize in Physics in 2022, 40 years after his experiment. He shared it with John Clauser and Anton Zeilinger. Zeilinger's group in Vienna had, over the decades, used entanglement to perform quantum teleportation, encoding and transmitting quantum states using entangled pairs. His group also ran one of the 3 loophole-free Bell tests in 2015. The Nobel Committee's citation for the 2022 prize read in part that the laureates had laid the foundation for a new era of quantum technology and for the exploration of entanglement as a physical resource. That word, resource, is important. Entanglement is not just a curiosity, it is what makes quantum computers work. It is what makes quantum cryptography secure. It is what allows quantum teleportation of information. The universe's deep structure is not just philosophically interesting, it is practically useful. Quantum cryptography uses entanglement to create encryption keys that are physically impossible to steal without detection. When 2 parties share an entangled pair of particles and use their measurement results to generate a shared secret key, any attempt by a third party to intercept and measure the particles disturbs the entanglement in a way that both parties can detect. The eavesdropper always leaves a trace. China launched the world's first quantum satellite called MICHIS in August 2016. By 2020, the MICHIS satellite had established entanglement-based quantum key distribution between ground stations separated by 1,200 kilometers, the longest distance over which quantum encryption had ever been demonstrated. The keys were provably secure by the laws of physics, not by the difficulty of a math problem. Quantum computers use entanglement differently. A classical computer processes information in bits, each of which is either 0 or 1. A quantum computer processes information in qubits, which can be in a superposition of 0 and 1 at the same time. When qubits are entangled with each other, the quantum computer can explore an enormous number of possible solutions simultaneously. For certain types of problems, this gives quantum computers an exponential advantage over classical computers. Google's Sycamore processor, in 2019, performed a specific calculation in 200 seconds that would take the world's best classical supercomputer approximately 10,000 years. That calculation was not useful on its own, but it was a proof that quantum advantage is real. Quantum teleportation uses entanglement to transmit the complete quantum state of a particle from one location to another without sending the particle itself. This was first demonstrated experimentally by Anton Zeilinger's group in Vienna in 1997, teleporting the polarization state of a photon. By 2022, Zeilinger's group and others had teleported quantum states across distances of over 1,400 kilometers using the MICHIS satellite. The particle itself does not move, but everything about it, everything that defines its quantum state, arrives perfectly at the destination, reconstructed from entanglement and a small classical signal. Einstein called it spooky. We now do it routinely with satellites. And here is something that very few people know. In 2015, the same year the loophole-free Bell tests were run, a physicist named Juan Maldacena gave a lecture at the Strings Conference in Bengaluru, India. He described the ER equals EPR idea and what it implied for the structure of the universe. At the end of the lecture, he said something that has stayed with physicists who were in the room. He said the lesson might be that the universe is not a collection of parts. The universe is more like a single quantum state, and everything we call a separate object is just a way of describing a part of that state in terms that are convenient for beings of our size and speed. He was not speaking loosely. He was describing what the equations say. Somewhere in the archives of the Perimeter Institute, there's a whiteboard from 2014 with equations connecting the entropy of entanglement to the curvature of space. The equations have been erased and rewritten dozens of times. The chalk lines are gone. But what they described is still sitting in the fabric of the universe, in the correlations between photons measured on opposite sides of a laboratory, in the polarization patterns of light that traveled for 13 billion years to reach our telescopes, in the behavior of quantum bits, simulating wormholes on processors, cooled to temperatures colder than outer space. The universe did not wait for us to notice. It was entangled before the first star lit up, before the first atom formed, before matter separated from energy separated from the quantum vacuum that held everything in superposition during the first fraction of the first second. That whiteboard is blank. The entanglement is not. It runs through the space between your eyes and the screen you're reading this on. It threads through the light that left distant stars before your ancestors were born. It was stitched into the fabric of reality in the first fractions of the first second, before time itself had settled into the steady rhythm we call physics. It is still there. It was never not there. And the physicists who spend their careers chasing it are beginning to believe that when they finally map its full shape, they will find that the map and the universe are the same thing.